Okay, it is 11 o'clock. First of all, PSA, a number of people sent me emails this weekend about the homework, which I did not see until this morning. So if you still have questions about the homework, you may ask them today or tomorrow morning. I will postpone the due date until tomorrow at noon. Um, if you have already turned it in but want to make changes based on questions you might want to ask today, and that's fine. You obviously have access to your Google Drive but I won't start taking the homeworks off your Google Drive until tomorrow at noon and having a look at them. There's an extension. If you have any questions, feel free to drop into office hours today or tomorrow morning, or send me. You've already sent me email. I will get to that email. I was just traveling this weekend and didn't see them. Um, okay, so we have been talking about systems which change over time. Where I give you an initial condition. And also transformation equations, propagation equations. So for example, let's take a look at the very simplest example we've looked at, where we had p sub 0 equals 1 and p sub n plus 1 equals 2 times p. So you have one, say, pair of rabbits at time 1, and at every time period after that, it doubles. So this says like 1 pair of rabbits initially, every time period it doubles. And as I said before, we've been treating time as if it were discrete. Time period 0, time period 1, time period 2, time period 3. We've been treating time as if it were a discrete variable. Here time is like n. And so far, our propagation equations have been linear. So for those of you that have already completed a linear algebra class, you know exactly what that means. And for those of you that are currently taking linear algebra, you have some idea of what it means because we've talked a little bit about it. We just talked about linearity in linear algebra this morning. But a linear function of just one variable x is basically just a number times x, 2x, 3x, 1/2 x, whatever. There aren't very many linear functions of one variable. Let me call it a. front of the x. A linear function.
What's the word after equations? Sorry, after have on the right side? Have.
So far, our propagation equations have been linear.
Oh, okay.
A linear function of just one variable always has the form just a times x, where a is some real number. So for example, f of x equals 2x. That's exactly what I used here. I just took my population at time n and multiplied it by 2 to get the population at the next time period. There aren't very many linear functions of just one variable. So a linear function of more than one variable let's say x1, x2, all the way up to xk, which I could write as a vector. I could write it x1, x2, all the way up to xk. I can write the function has this form, a times x, where a is an appropriately sized matrix. Oh, sorry, k by k matrix. I said this has k entries. That's k. And we've seen examples of that. We've seen examples where we had like a 2 by 2 matrix. Systems with linear propagation equations can have various kinds of behavior. We've already seen some. We've seen systems like that first one that had steady growth. If you have a population of rabbits and they double every time period, you have steady growth. I mean, exponential growth, basically. You've seen examples which decay steadily. You've seen examples where the populations, we were talking about populations, they approach a steady state. Or equilibrium. We saw last time an example where there was growth for a little while and then it started to decay. And there are other kinds of growth, there are other kinds of behavior that you could possibly see, although not as many when we're talking about population examples. We'd have to be talking about some other kinds of things. So there are a few other kinds of behavior we could see. If I picked out an appropriate example, you might see oscillation. But really, there aren't that many possibilities when it comes to systems with linear transformation functions. Propagation equations don't have to be linear. And in general, when they're not linear, we can expect more complicated behavior. Oh, sorry, if they are not linear. So you've seen several examples, all of them linear so far. And so we've seen a few kinds of behavior. Let me give you an example. This is not going to have particularly complicated kind of behavior. So let's see. Let's say, we'll stick with population right now. It's an easy one to visualize. Let's say P of 0 equals 2,000. And let's say P of n plus 1 is equal to 1/2 times population at time n plus 1,000. So without that plus 1,000, this would be linear. But with the plus 1,000, it's no longer linear. It's not a linear function. It's what's called an affine function, but it's not linear. So let's make up a little chart. I think you'll see what's going on here very quickly. So n population at time n. So when n equals 0, it's, what do we say, 2,000. Put in the next few numbers until you decide what's going on. I don't think this is going to take you very long.
It's going to stay the same, right?
It just stays the same, right? So, so what we have here is sort of steady state This is definitely an equilibrium. Let me give you the same. Here's example 1. Example 2. I'm going to change the initial. I'm going to change the initial population. I'll change it to 1,000. But I'll keep the same propagation equation. Pn plus 1 equals 1/2 Pn plus 1,000. Same propagation equation. All I did is change the initial condition. Oops.
Oh,
It's a like a non like a slowly decreasing increase.
Yeah, absolutely.
so it's going to approach 2,000, right?
Approaching 2,000 again. After time period 1, 1/2 of 1,000 is 500 plus 1,000 is 1,500. 1/2 of that 750 plus 1,000 is 1,750. 1/2 of 1,750 is what 800 and what 75. So 1875. After that, it's goes decimal. That's okay. So after 4, what 19. Let's see, 62.5. So what 37.5. So we'll have to imagine if this is a population that can't quite be right, but we'll somewhere around there. And so on. And these numbers are getting closer and closer to 2,000. So those are getting closer and closer to 2,000. Let me give you yet a third one. I'm going to keep the same propagation equation. But this time I'll start you at, how about 4,000?
Slowly approaching 5,000, right? Or no,
No,
no.
it's still approaching 2,000,
I think it's
but in
still,
the opposite direction.
yeah.
Sorry.
So 1/2 of 4,000 is 2,000 plus 1,000 is 3,000. 1/2 of 3,000 is 1,500 plus 1,000 is 2,500. 1/2 of 2,500 is 1,250. So this is 2,250. Then 2,125. Oops. Let's see, it's 60. So 2,062.5 and so on. These are going again towards 2,000. Does everybody get the feeling that no matter what you start with, you head towards 2,000 eventually with this propagation equation? Is that your general sense? That's correct. So not only 2,000, so 2,000 is an equilibrium. Say P equals 2,000 is an equilibrium. 1 point. It's a specific kind of equilibrium point where things tend to go towards it. It's called a stable equilibrium. For those of you that have taken differential equations, this will all be familiar terminology. So it is a stable equilibrium. Things tend to move towards it, at least nearby things. Is that okay? Let's draw ourselves a picture. So, let's see. I'm just going to call this X. I'm going to call this Y. Please forgive me my lack of imagination. And I'm going to mark some points on here. I'll make that scale on here. This is 1,000. This is 2,000, 3,000, 4,000. Let me try to put the same scale here. 1,000, oops, 1,000, 2,000, 3,000. And on this picture, I'm going to put in 2 lines. I'm going to put the line y equals x. And y equals x, of course, is just the line which goes uphill at 45 degrees. It goes through the point 1,000, 1,000. It goes through the point 2,000, 2,000. Of course, it goes through 0, 0. It's the line which goes uphill at 45 degrees. No, You don't look like a straight line on my picture because my drawing is terrible. And I'm going to put in another line. This one I'm going to draw with a solid line. I'm going to put in the line y equals 1/2 x, 1/2 x plus 1,000. Numbers right here. So this is a line with y-intercept 1,000, slope 1/2. So we go over 1,000, you go up to 1,500. You go over another 1,000, go up to 2,000 and so on. So let me do my best to sketch that. Here is y equals x, and here is y equals 1/2 x plus 1,000. So let's say, is everybody finished copying? I know copying always takes longer than me drawing. Let's see, we start off with a number, I don't know, how about 1,000? So on the x-axis, we'll go to 1,000. To figure out what the next number is in our sequence, you plug it into the line 1/2 x plus 1,000. That's how you got this. You took 1/2 of 1,000 and added 1,000. 1/2 of 1,000 is 500 plus 1,000 is 1,500. So in other words, at 1,000, you go up to the line, and the y value here is 1,500. That's the next number I want to plug into that line. So I want to turn that from a y value into an x value. To turn it from a y value into an x value, I go over to the line y equals x. That's what y equals x does. So now I'm at 1,500, x equals 1,500. Got to figure out what the next number is. I go up to the line again. Now I'm at 1,750. I'm going to want to plug that back into the line, so I want to turn it into an x value. That's supposed to be vertical. So I go to the line y equals x. And now I'm at 1,875. My x value is, it's still at 1,750. And now I go up to the line, I'm at 1,875. Back and forth, zigzag, zigzag. You can see I'm getting closer and closer to 2,000. This is sometimes called the spider web. If I start off at 4,000 and I go up to the line 1/2 x plus 1,000, I'm at height 3,000 suddenly, even though it doesn't really look like it on my picture. I'm at height 3,000. I go over to the line y equals x. Now I'm at x value 3,000. I go to the line. Go to the line y equals x. Go to the line y equals x. Go to the line. And I'm getting closer and closer to 2,000. From the left or from the right. You can see, looking at this picture, that I have a stable equilibrium at x equals 2,000. All these spider webs approach that point. Does everybody see what's going on here? Cool. Okay. Just out of curiosity, have you done this before? Is this new? Okay, in that case, it's my privilege to share it with you. This can come up in a variety of different classes, but if it hasn't, then it's my privilege to be able to share it with you for the first time.
Is there something to indicate that an equation like that would be a stable equilibrium equation before you see it?
What a splendid question. Yes, and we'll come back. I think before we're finished here, you might have some idea of what it is. And if you don't, I'll tell you. But you'll remember it longer if you come up with it for yourself. So how about we do this? How about I give you this propagation equation? Pn plus 1 equals -1/2 Pn plus 1,000. Hang on, is that what I want to do? Yeah.
So
Yeah, go ahead.
So to find the equilibrium, we would just have to have Pn plus 1 equal Pn. And
Great. Let's find the equilibrium point. We use Jackson's suggestion. If we're at the equilibrium point, then Pn plus 1 is the same as Pn. In other words, we're looking for the line where y equals x crosses whatever this curve is. So we will set Pn equal to negative 1/2 Pn plus 1,000. We can add half Pn to both sides. So I end up with 1/2 Pn equals 1,000. If I multiply both sides by 2, I get Pn equals 2,000. So 2,000 is definitely an equilibrium point again. If I put 2,000, wait a second, did I mess up? Yes, I did. Sorry about that. I can't do arithmetic. So if I add 1/2 Pn to both sides, I don't get 1/2 Pn. I get 3/2 Pn. And so my Pn is going to be 2/3 times 1,000, or it'll be 2,000 over 3, or about 667-ish. So let me give you a P naught, and you can compute the first few numbers you get. Let's say P naught equals 1,000. So minus 1/2 times 1,000 is minus 500, plus 1,000, that's 500. Minus 1/2 times 500 is negative 250, plus 1,000 is 750. So minus 1/2 times 750 is what? 370 minus 375 plus 1,000. What did I say? 375. So that's what? 625. And so on. So this time the numbers are sort of bobbing up and down, 1,500 and up to 750, 625. And we know they're getting close to 667 or 666 and 2/3. Let's draw a picture. And if it wasn't clear before why this is called the spiderweb method, it will be now. So let's see, how about so here is, let's say, 500, here's 1,000, 500, 1,000. And the line y equals x goes through 500, 500. It goes through 1,000, 1,000. I'll just dot that in. Sorry that I can't draw a straight line for the life of me. And the line minus, the line y equals minus 1/2 x plus 1,000 crosses the y-axis of 1,000. Has slope minus 1/2. So let's see, if I go over 1,000, I go down to 500. And so that line looks like this. Again, that's supposed to be straight. So y equals minus 1/2 x plus 1,000. And we know these two lines cross at like 667. So if, for instance, I start off at 1,000, I go up to the curve. I'm at height 500. That's the next number I want to plug in. So I go over to the line y equals x. Then I go up to the curve. So here I am at 500. I go up to the curve. I am now at height, 750. I go to the line y equals x. I go to the curve. The curve, by that I mean this line here. I go to the line y equals x. And so on, and so on, and so on. So I have another stable equilibrium. This again turns out to be stable equilibrium. Is it clear that this is stable, that things are going to tend to move towards it in this particular picture? Is it also clear why this is called the spiderweb method? Looks like a spiderweb to me. Well, kind of. Spiderweb-ish. Okay, well, let's take a look at another one. How about we do a propagation equation, n plus 1 equals 2pn plus 1,000. Sorry, not plus 1,000, minus 1,000. 2pn minus 1,000. So we can use Jackson's suggestion to figure out what the equilibrium point or points are. So we'll set pn plus 1 equals pn to find the equilibrium point. So pn equals 2pn minus 1,000. I can subtract pn from both sides and add 1,000 to both sides, so I end up with pn equals 1,000. So that is an equilibrium point. If I plug 1,000 in, I will keep getting 1,000. So P0 equals 1,000. Then the next one is going to be 2 times 1,000 minus 1,000 is 1,000. The next one is going to be 2 times 1,000 minus 1,000, that's going to be 1,000, and so on. So it's definitely an equilibrium point. Let me give you another initial condition. How about P0 equals 0, blah, 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 blah. How about we make it 1,002. So 2 times 1,002 is 2,004, minus 1,000 is 1,004. 2 times 1,004 is 2,008, minus 1,000 is 1,008. 2 times 1,008 is 2,016, minus 1,000 is 1,016. And 1,032, and then and so on. What if I gave you P0 equals 999? Two times 999 is 1,998 minus 1,000, which is 998. 2 times 2 times 998 is 1,996 minus 1,000 is 996. And the next one would be 992. The next one would be 9,000. Sorry, it would be 984, and so on. So we know 1,000 is an equilibrium point. What kind of equilibrium is 1,000?
Unstable equilibrium.
Definitely unstable.
Equilibrium, sorry.
No, you're absolutely right. It's an unstable equilibrium. So unstable equilibrium point. And let's take a look at the picture.
Why is it an unstable equilibrium point?
Because things are moving away from it. Like if I start at 1,002, it's moving away from it. And if I start at 999, it's moving away from 1,000. Things tend to move further away from 1,000. Was that Wade who asked that question?
Yeah.
Okay. So are you asked, did you mean what the definition of equilibrium, unstable equilibrium was, or did you mean how would you know?
I meant how would you know, and you answer my question.
Okay. Yeah. So, but I still want to come back to your previous question, which was how could you know in advance that the previous examples were stable and this one was unstable? And I'm wondering, after this example, if some of you will start to have some hypotheses about that. So if I put in the line y equals x, well, let me put that in a second. 500, 1,000. And we have the line y equals x. And we have the line y equals 2x minus 1,000. So let's see, that crosses the axis at 500 and crosses here at 1,000. So one that looks like that. So here's the line y equals 2x minus 1,000. If I start somewhere and I go up to the line and then go to the line y equals x and then go vertically to the line and then to the line y equals x, here you can see I'm moving away, moving steadily away from 1,000. And it's the same on the other side, even though my lines as usual are not straight in my picture. Apologize for that. If I go up to the line and then go to the line y equals x to the line to y equals x, again, I'm moving steadily away from 1,000. Even though 1,000 is an equilibrium point. Do you have some hypotheses?
It's like balancing one ball on another ball.
Well, that's certainly true. That's an excellent description. That is definitely an unstable equilibrium. So what Jackson just said is it's technically possible, well, sort of, if you have a ball and you put another ball right on top of it, if everything were perfectly balanced, that ball up here would stay on the ball below. But it's an unstable equilibrium. Any minute movement of that second ball in one direction or the other, and it falls off. Right? Does anybody here ever balance an egg on its end? You do not have to wait until any sort of astronomical event to do this. It is totally possible to balance an egg on its end if you are patient and careful. It's very frustrating, but possible. But it's an unstable equilibrium. If you balance an egg on its end, the thing is that the shell has these little tiny dimples in it. If you find the right dimple, you can do it. Has anybody ever balanced a salt shaker on its corner? So you have like a salt shaker and you balance it.
I mean, I did with a soda can.
So a salt shaker, this is kind of a cute. I'm sort of amazed that you haven't done this in the dining hall before, because this is sort of a classic college thing. Can you balance a salt shaker on its corner? What you do, it's a trick. You take the salt shaker and you sprinkle some grains of salt down here, and then you balance the salt shaker in there, and then you blow away most of the grains. So there's like 3 grains holding up the salt shaker. It's cute. When you get back, you can do it. If you have salt shakers at home, which you certainly do, you can try it. But the salt shakers on a college campus tend to work very well for that. Anywho, but they're all unstable equilibriums. Even if you manage to balance an egg on its end, if there's a wind or anything gets disturbed, it's going to fall over. Same with the salt shaker. But this is definitely an unstable equilibrium. If I start at 1,000, I'm going to keep getting 1,000. I'll get 1,000, 1,000, 1,000 forever. But if I start a little bit above or below, I tend to move away from 1,000. So is everybody okay with the idea of what a stable and unstable equilibrium are? Does anybody have hypotheses yet as to what makes this one unstable, but the previous example stable? So far, I've only used these straight lines, and straight lines are a great way to start getting a feeling for this. What makes these ones unstable and the other ones stable? Straight lines don't have that many properties. So one of them is the one you need.
Is it the slope?
It is the slope. So what's true about the slope of this as opposed to the slope of the other two?
If it's greater than 1, it's unstable. If less
Pretty,
than 1,
pretty much. Jackson, is that what you're going to say too?
Well, I was just gonna say that the y-intercept is below
That's true.
the origin.
And for a straight line, you may be able to make some connection with that. I want to think about what you just said, because I'm not sure. But what I had in mind actually was the slope. If you have a straight line and the absolute value of the slope is greater than 1, it's unstable. And if the absolute value of your slope is less than 1, it's stable. Now, since you've all gone through calculus, you might start to make some hypotheses about what may or may not be true if your curve isn't a straight line. So far, I've used the curves that are straight lines, even though these are not linear curves. These are affine curves. So what takes the place of slope when you have a curve rather than a straight line? Starts with a D and ends with derivative.
The derivative.
Yeah, right. Excellent. So there's a lot of I'm sure right now hypotheses are swimming through your head, and some of them are true. Probably many of them are true, and some are not quite as true as one would hope. But yeah, we could definitely make similar statements about the derivative, and we will. But I see we're just about out of time. In fact, I've already gone over time. I apologize for that. Have a good rest of your Labor Day, and I will see you all on Wednesday. I will have office hours this afternoon, and I will have office hours tomorrow morning in case there are questions.